Alright, welcome back everybody. In this video we're going to look at examples 3 and 4 from the areas involving polar curves lesson. We'll start with example 3. We're going to determine the area of the region outside of the curve r equals 3 plus 2 sine of theta and inside of the curve r equals 2. So we can set up our integral a while if we think about it. We've got 1/2 times the integral, and our outer curve is going to be the curve that we have stuff inside, and our inner curve is going to be the curve that we have stuff outside of. And now we just need to figure out the limits of integration for this. And we already have our graph of these two curves. And so when we're finding the area of the region outside of the big curve and inside of the small curve, what we're looking at is this area right in here. And so we need to find the theta values where these two curves intersect, those two spots right there. Alright, so let's go ahead and do that. We'll find those intersection points. We go to our calculator and we're going to trace this. And the first intersection point here, well, I'm going to trace around the curve. Oh, I already got to the end because I only graphed from 0 to 2 pi. We go back to here. They intersect right here at 3.6651914. So that's going to be 7 pi over 6. We actually found these intersection points in the last example. And the other intersection point is over here at 11 pi over 6. And so there's our integral that we're going to use to find the area inside that region. Alright, so let's go ahead and we'll take 1/2 times the integral of 2 squared minus the quantity 3 plus 2 sine of theta squared with respect to theta from 7 pi over 6 to 11 pi over 6. And it says here that that area is 2.196. Alright, there's the area of the region outside the big circle and inside the small circle. Alright, last one here. The area that is inside both of these curves. So if we look at the graph again, and we want the area that's inside both of those, we're actually looking for this area in here that's inside both of them. Okay. And there's not a neat single integral formula that I can use here, because it's not really the region between one of those curves and the other one. It's really the area inside one of those curves and then the area inside of the other. And so what's actually the simplest way to do this, we just found the area of the region below that one. What we can do is we can take the area of the small circle and subtract away the area of this region down here, and that gives me the area of the region that I want. Okay, so we'll go back to our scratch sheet here, and all I'm going to do is I'm going to take the circle, the small circle, which has an area of 4, and subtract away the area that we just found of the small region, Does that just not seem like it's going to give us the right value? Feels like that should be bigger. Oh, area of a circle is not just the radius squared. It's pi times the radius squared. Haha. Hate it when my mind plays tricks on me. That'll be much better. We're going to take the area of the small circle minus the area of the region that we just found. And that's going to give us our area for the region in question here. So I've got this area, and I'm going to take pi times 2 squared minus my previous answer. And I get that the area of this region is 10.370. So something that's illustrated by these examples is we don't always necessarily just use a straightforward integral formula. We sometimes are going to need to adapt our situation depending upon the region that we're trying to find. And so you want to be really meticulous with looking at the curves that you have and which exact region you're trying to find the area of, and then come up with a reasonable, sensible model for how to acquire that region. That area is the region of that, the area of that region. Sorry, I forgot how to talk there for a second. And sometimes when we do that, we're going to have to, use combinations of two different integrals, depending on what region we're looking at. We might have a difference of two integrals. We might have the integral of the difference of two things. We might have the sum of two integrals. It all really depends on the situation that you encounter. And the best way to get good at these is by encountering as many different scenarios as you can. So get to work and do some problems and see if you can get very good at finding the area between the areas here involving these polar curves. Alright, that's it for this video. See you guys next time. Have a great rest of your day.